Right, we are in section 9.1. We're going to do we'll do another part of 9.1 on block day. And block day, we're going to, because of the rain, block day we're doubling up on a lesson, unfortunately. But both parts, neither part are particularly long or particularly difficult, so it shouldn't be too bad. All right, so we're talking about sequences. Now, we've all seen sequences before. We've all used sequences before at one time or another. When we're talking about a sequence, what are we talking about? What do we mean when we're talking about a sequence? Anybody have an idea? We've all worked with them.
Horrible, awful thing.
Horrible, awful things. Well, I'm just going to write down something. That doesn't look too horrible or awful, does it? So a sequence. What are we talking about? Go ahead.
It's a series of numbers that have a certain change that happens from each number to the next.
Okay, so we're just talking about a list of numbers that just have some kind of relationship between them, right? So that kind of an everyday word. We're talking about a list of numbers. The way I think of it, and the way I wrote it here, we put them in order. So we just have a list of numbers in order, some collection of numbers in order. Now, we're going to be just make that a little more formal, and we'll make our definition, the definition that we're going to use, and that makes them nice to work with, because we relate it to something that we're more familiar with in math, is a function. We like working with functions, whose domain is the set of positive integers. So we have a function and we plug in positive integers to get our values. That's usually how we think of a sequence. We can plug in a 1, a 2, a 3. We get our list of our list of numbers, and we usually write them in subscript notation rather than function notation. So we would say a sub 1, a sub 2, a sub 3, ... all the way to a sub n, whatever n, however many we're talking about. And we call these are the terms of the sequence. The terms of the sequence are the individual a sub n. And then we write the entire sequence with braces. So this would be the entire sequence. So we have the terms, we have the entire sequence. Now we can have a function that we plug in positive integers into and get our sequence. We can also have another type of sequence, a recursive sequence. So what's different about a recursive sequence? How is that different than what we just talked about here? We define a sequence recursively. Anybody have an idea? So a recursive sequence has something to do, each term has something to do with one or more of the terms before it. So we need one or more of the previous terms to get a current term. So our subsequent terms are defined in terms of previous terms. So And I'm using terms in two different ways here. Terms are defined in terms of previous terms. So we get to use that word terms a lot there. What would be an example of a recursive sequence that we have generated in this class very recently? Newton's method. Newton's method, we plug in this function that's defined in terms of our previous guesses. We had to start with some initial guess. We plug it in, we get a new guess. We plug the new guess in, get a new guess, and we get a sequence of approximations to the zeros of our function. Fibonacci sequence is a recursive sequence. Yes, that's probably the most famous recursive sequence is the Fibonacci sequence. So for a recursive sequence, we're defining it in terms of its previous term. So let's let me write out an example of a recursive sequence, and we'll calculate some terms. So let's say that a sub 1 equals 3. So we're defining our first term as 3. And a sub k plus 1 equals 2 a sub k minus 1. So this is my definition for my recursive sequence. I have a first term. The subsequent terms are defined in terms of the previous term. So for this sequence, what would a sub 2 be? What is it?
4.
4. So I plug in 3 here. 3 minus 1 is 2 times 2, and I get 4. And then a sub 3, 6. So I plug in 4 into my formula, previous term, and calculate. So I get 6, a sub 4, 10, etc. So my sequence. So the sequence is 3, 4, 6, 10, ... That would be the terms of the sequence listed out. So we just use our previous terms to calculate our current terms. Are we all good with that? We're kind of easing into sequences. So hopefully they're not horrible, terrible things yet anyway. All right, I have some sequences and some graphs of terms of sequences I want to look at, and we're going to match the graph to the sequence, to the definition of the sequence. Let me grab those. So we want to, for these, we want to match the graph. So these are the graphs of terms of each of these sequences. We want to match the graph to the terms, or to the definition of the sequence, and maybe talk about how we came up with that idea. So how about number 9? We have 10 over n plus 1. So if we graphed out those terms, what graph would we get? C. And how did we decide?
It looks like it's converging to 1 as we go towards 10.
Converging to 0, right? The limit, because of the bottom goes to, as n gets very large, the bottom goes to infinity. So we should converge to 0. So let me write that in. Got that one right? C. No, explanation point. We're excited. We got C. Awesome. We'll talk about factorials later. So I don't make you nervous. I'll raise the exclamation point. All right. Number 10. So number 10 is similar. 10n over n plus 1. A. We have a smattering of A's. A?
Yeah.
Do we agree?
Yeah.
Okay, how did we decide on that one? Converges to 10, and how do we know that that sequence would converge to 10? Okay, so we can look at the limit as the limit of each term as n goes to infinity. The limit 10n, and Max is saying we can ignore this 1. We could also think of, you could think of it in terms of your, if you think of this as a rational function, your horizontal asymptote is the ratio of the leading coefficients, same idea. So this would converge to 10. So what is this, A? Can I put a tiny exclamation point? Or the top part is a little bigger now. All right. How about number 11, minus 1 to the n? D? Because what does that do? What happens is I plug in n? Just alternates between positive and negative, right? So we got D with a little exclamation point. Right. And then that only leaves B for 12. Now, if we started with 12 and we hadn't looked at any of the others, we hadn't used the process of elimination to get 12. What's a procedure we could use? How could we think about that one? Converge it to 0, but the minus 1 to the n makes it do what? Alternate signs. So it starts out and then converges to 0, but it's kind of bouncing back and forth across the x-axis. So this is going to be B. See, they're not horrible, terrible things. They're kind of nice things. All right. Now we need to talk about, so probably the most important idea in all of calculus. The limit of a sequence. And that's another reason that I really like this chapter, is because the idea of sequences and series, convergence and limits, that is really the foundation of calculus, is limits and convergence. That's what calculus is built of. So our main concern, our main goal of the entire chapter, all of chapter 9, is to talk about sequences and whether or not they approach a limit. That's really our goal. So let's remember and I know you all have seen this. Let's remember the definition of the limit of a sequence. So we're going to say L is our limit. L is a real number. When you start talking about limits of complex sequences, then things get really interesting. So we're going to say the limit. I'll start us out. Of a sequence. I'm going to move this down so I can put my equal sign here. The limit of, let me redraw that race. The limit of a sub n equals L. Or we can write either of these two terminologies work. If we remember our definition, has to do with two lovely letters. Or someone said it. For each, what's our letter? epsilon, no matter how small, for each epsilon, no matter how small, whoops, there exists a, what's our other letter? There exists a delta. We're going to say, for the, rather than delta, since we're talking about a sequence, we're going to say there exists an m. Because we're not talking about the limit of a function. There exists an m greater than 0, but you guys were on the right track for the limit of a function. We use epsilons and deltas. There exists an m greater than 0 such that the absolute value of a sub n minus L is less than epsilon if n is greater than m. So this is our definition of the limit of a sequence. If this limit exists, then the sequence converges. And if the limit does not exist, then the sequence diverges. Now you'll be thankful because we're not going to do epsilon proofs for sequence convergence. I just wanted to remind you this is our definition. This is what makes the idea of a limit rigorous. Any other definition of a limit is more hand waving, kind of intuitive. This is what makes it mathematically rigorous. What it's telling us is we can pick an epsilon, a tiny epsilon. I think of it as a challenge number. And we want our terms of our sequence to be within that tiny challenge number of the limit. What that tells us is we can find an m, go out further and further and further in our sequence, such that once we get above that m, that our sequence is always within that tiny epsilon of the limit. So it means that as we get really large, our sequence stays really close. The terms of the sequence stay really close to the limit. It's not a complicated idea. It's just this is how we have to make it, that idea of closeness, this is how we make it rigorous. This is how we, kind of the mathematical definition of close, as close as we want. And if we drew a picture of this graphically, what we're saying is we have our, I'll put the L in red here. There's L. And our challenge is epsilon. So I'm going to put our epsilon in blue here. So this up here is L plus epsilon, and the blue line down here is L minus epsilon. So we're talking about the absolute value, so we can be on either side of L. And on the x-axis we have our n's. So we have 1, 2, 3, and we go dot 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 to m. And our sequence, the terms of our sequence for 1, maybe it's here, I don't know. where it would be. Maybe for 2, whatever our sequence is down here. For 3, our sequence, the third term of our sequence is there. And then we end up getting here. I'm just making this up. And then once we hit M, the terms of our sequence are always inside that blue band. So the green dots are my A sub n's. So graphically, it just tells me that eventually that the sequence, the terms of the sequence are within this blue band, are close to that limit. And the definition of the limit tells us that if we pick an epsilon, that if we can find an m that guarantees that eventually our terms are within that distance of L. So that's what it's telling us graphically. Not a complicated idea to think about. Sometimes to work with that definition of a limit is a little more challenging. Well, that's our definition of a limit. Yes. So then, if the limit was 0, then L would be down here on the axis, and then our band would just be up above and below the x-axis. Okay? So the way we're going to work, I'm not going to make us work with this definition of a limit. We defined our sequence as a function of positive integers. So we're going to use what we know about functions to determine the limit of a sequence. Because we're familiar with techniques for finding limits of functions. We talked about a couple of them when we were looking at the graphs. So we're going to say that f is a function. Such that the limit as x approaches infinity of f of x is L. If our terms if f sub n equals a sub n for all of our positive integers, then we can say that the limit as n approaches infinity of a sub n also equals L. So we're going to use, basically what we're going to do is use what we know about limits of functions to find limits of sequences. So we've developed, we're assuming that we've developed a way of working with functions, finding limits of functions, which I know we have. So we're going to use limits of functions to find limits of sequences. We're going to use what we know about functions to find limits of sequences. Properties of limits, I'm not going to write all the properties of limits down. We know properties of limits. If we can multiply by a constant, we can add or subtract limits. We can multiply the limits of two sequences. We can divide the limits of two sequences as long as our denominator is not 0. So we're familiar with properties of limits. So we can use those when we're talking about sequences. So if we have a sequence that we can break down into the sum of two functions, we can find the limit of each function individually. We can break it down into the quotient of two functions. We can find the quotient, the limit of the numerator and the limit of the denominator, and work with them that way. So, not a bad way to ease into sequences. Nothing too mathematically overwhelming. Nothing too terrible. All right, not yet. Okay, so that's all I had to say today. We will talk more about sequences on block day. We'll talk about bounded and monotonic sequences. And then we will talk about how sequences are related to series. We'll make a relationship between sequences and series. So our homework, page 592. All right, and even not a particularly painful homework assignment.
Shorter assignments sometimes are the harder ones.
You think?